Quake, the groundbreaking first-person shooter from 1996, was one of the first games to popularize speedrunning. Despite being released almost 24 years ago, it still has an active community of players. Records are still being broken on a variety of maps, and techniques are continually being refined. One of the main techniques used by speedrunners is strafe jumping. This is a method of gaining speed beyond the limit intended by the game's developers. As such, strafe jumping is a bug in the Quake physics code, which over the years has been refined to be very fast indeed. To see how fast, let's compare the world record time on the 100-meter level, a community-made practice map, to a run which doesn't exploit any physics bugs. I've covered the reasons behind the strafe jumping bug in Quake 3, a later game in the series, in a previous video. The physics for Quake are very similar, so check it out if you're interested. For now, it is enough to know that it involves repeatedly jumping whilst manipulating the mouse and direction keys in a particular way. In this video, I want to talk about how I trained a reinforcement learning agent to strafe jump the 100-meter map using RLLib. So what exactly is reinforcement learning? It's a technique for training a policy to maximize rewards obtained from interacting with an environment. The policy makes observations of the environment, applies actions to it, and gets a reward and a further observation. Each action-reward observation cycle is known as a step, and numerous steps are taken until the environment indicates that it is done. This entire process is known as an episode. The goal of reinforcement learning is to produce a policy that selects actions based on the observations it has seen so far in order to maximize the expected reward it will earn in the future or the near future. Learning takes place by evaluating many episodes and incrementally refining the policy to choose actions which give the most future reward. The whole process is orchestrated by a trainer which watches outputs of both the policy and the environment and updates the policy. In this case, the environment is the relevant parts of the Quake physics code ported into Python. Each step corresponds with a single physics frame in Quake, which runs at 72 frames per second in-game. At each step, inputs are taken in the form of encoded key presses and mouse movements. The inputs are processed by the physics engine, and a reward is given based on how far the engine says the player travelled in that frame. I set the done flag at 720 steps, or 10 in-game seconds. So in order to maximize reward, the agent should learn to travel as far as possible in that time. In practice, the environment is implemented by subclassing gym.env, which is a standard interface provided by OpenAI. The environment must define an action space and an observation space, which specify the format of the actions passed into the environment and the observations passed out. In other words, it defines the interface between the policy and the environment. In this case, the action space is the direction keys, the jump keys, and one mouse dimension. This means that at every step, the policy will produce a vector of 5 floating point values encoding the key presses and mouse movement information that will be passed into the environment. The observation space is anything that should be useful for the policy to know which actions to take. In this case, I pass the time remaining, current angle the player is facing, and position and velocity information to the policy. As with the action space, this is represented as a vector of floating point numbers. The vector is returned from the environment. The central part of the environment is the step method, which accepts an action vector in the format described by the action space, and returns an observation, the reward for this step, and whether or not the episode has finished. In this case, the implementation decodes the actions, passes them through the physics engine, and calculates the return values. And what about the trainer? How exactly does it maximize the rewards earned by the policy? This is what the field of reinforcement learning is all about, designing an algorithm that can train a policy to perform well given an environment class like the one we just talked about. Fortunately, RLLib provides implementations of many state-of-the-art algorithms that do this. They cannot be treated entirely as black boxes, however, and some degree of knowledge is required to know which algorithm is best for a given situation. Furthermore, each algorithm comes with a set of dials to adjust, known as hyperparameters. Again, some understanding is required to know how to change the hyperparameters to improve the agent's performance. So let's take a look at how it performs. I started out with a simpler problem than the one described above, and ramped up the difficulty bit by bit. In the first iteration, I allowed only moving side to side and forwards, with no ability to jump. Once trained, we can see that it learns to rapidly alternate between pressing left and right whilst holding forwards. This is known as zigzagging and was one of the first physics bugs to be exploited in Quake, featuring in some of the very early speedruns before strafe jumping was discovered. Unfortunately, as a result of my Python physics code modelling the world as a flat plane, the agent ends up colliding with a floodlight when it's applied to the real game. Nevertheless, you can see that by zigzagging the agent still achieves a speed above the developer-intended maximum of 320 units per second. Note that to make the inputs a little more human-like, I've restricted the rate at which keys can be pressed. Specifically, I stopped a given key press from being registered if it had been pressed within the last 0.3 seconds. This is the reason that the learn policy only changes direction a few times a second. Next, I wanted to see if it could learn to travel while jumping. To keep things simple, I modified the agent to hit the jump key whenever it is approaching the ground. As such, the agent doesn't need to concern itself with learning how to travel on the ground, or when to press the jump key. It does, however, have the ability to move the mouse up to 10 degrees per frame, so a maximum of 2 rotations per second. Here you can see it has learned a behaviour which looks similar to strafe jumping. Let's analyse this further. By reading the Quake physics code, you can work out that the amount the player accelerates in each frame depends only on two things: the player's velocity, shown here by the green arrow, and the player's wish velocity, which is shown here by the blue arrow. The wish velocity is the direction the player is facing combined with the direction keys. In fact, as long as the player is holding one of the direction keys, then the physics just depends on the angle between the two arrows. Finally, when on the ground, friction is applied, resulting in slightly different physics. Because the only thing within the agent's control on a given frame is the wish angle, then we can use our physics code to simulate how much we would have accelerated with a wish angle at a particular value. Here is a plot of one of the auto-jumping agent's episodes. The dashed magenta line shows the velocity to wish velocity angle that the agent actually selected. The colours in the background indicate which angles would have resulted in the biggest increase in speed. As you can see, the agent does a good job of finding the regions of most acceleration. You will notice that there are regular single frames where the optimal velocity is different. These are the frames between jumps where the player is treated as being on the ground, hence friction is applied, resulting in a different optimum. This is very important as the player can lose a lot of speed on this one frame, and so it is crucial that the player hits the right wish angle while on the floor. Speedrunners normally deal with this by briefly tapping forwards around the time when they hit the ground, and it appears as though the agent has learned to do the same thing. This technique is known as power bunny hopping and is one of the fastest known methods of moving between 2 points without any outside forces. For the final version, I gave the agent the ability to press the jump key, so it has full control, and as a result it does much better. The reason for this is that when going at low speeds you can actually accelerate more on the ground than in the air. It is only as you start moving faster that ground friction grows large enough to overwhelm the extra acceleration. Furthermore, even while on the ground you can gain some extra acceleration by controlling the wish direction relative to your move direction, just as happens in the air. This technique is also used by speedrunners to gain some initial speed before entering into one of the other techniques. And so how does it compare with the world record at the time of recording? Let's do a head-to-head race. This is where I am with the project so far, and although it has taken many hours to program, I am pleased that it managed to exploit a few of the physics bugs that speedrunners use, just with me providing an environment for it to play in and an off-the-shelf algorithm with a few hyperparameter tweaks. Some of the techniques, power bunny hopping in particular, took many years for speedrunners to discover. I wonder if these tools had been available back then, could reinforcement learning have found these techniques before humans? It is worth noting that although the agent beat the human record holder, it is able to cheat in the sense that it doesn't have to deal with the limits of human observation and motor control. Even with the limitation on key press rate and absolute mouse speed, the agent can still play with complete precision within these bounds and can observe speed and velocity more accurately than a human could. In terms of possible improvements, it would be good to fine-tune some of the mechanics. Although it has learned the same mechanics as the best speedrunners, the execution is not perfect, and the agent still throws in apparently random actions every now and then, which impede performance. On the other hand, perhaps these aberrations are unavoidable or even beneficial in some way. It would be interesting to see how a handcrafted agent would compare, both with and without the key press restriction. After this, I would like to extend the agent to more complex levels. How would this work? The agent has already been taught to run in a straight line in a particular direction. Given a path through a level, it should not be much harder to have the agent follow that path instead. Of course, there are both technical and reinforcement learning issues to overcome here. For example, my simple physics simulation would no longer be adequate, and it would probably be best to integrate directly with Quake, which would require more work. Designing a reward function so that the agent learns to press a button to open a door, for example, could also be tricky. On the face of it, these issues are all surmountable, so it'd be an interesting avenue to explore. I hope you found this video enjoyable. If you did, please click like and consider subscribing. As always, please leave a comment if you have any questions.